forgive me. And so I said, okay, so how about a differentiable function into an? So look at that. That by definition is this. Well, I mean by advanced calculus is that. But then I can pull y out of each one, right? And then I can put it back together. Oh, look at that. So in fact, right linearity for each component function implies right linearity for the whole thing. I probably could have used that as a definition for differentiability of the function from a into a prime, just the same. I could have said it's real differentiable and its differential is right alinear. That would imply a differentiability of all the component functions, and that'd probably be a better definition. But, you know, I don't think too hard about what's the most awesome definition when I write this stuff. I try to come up with working definitions. It's a working definition. Anyway, and the derivative is, you feed it 1. So, yay. That's kind of a nice extension of what we've already done. You're like, well, that's wonderful. What does that have to do with what you were talking about a minute ago? What does that have to do with any of this? This differential equation stuff, right? Well, my next thing is that if we have a function from a to a prime, a differentiable, and I have another function from a prime to a prime, right? So if I got a function on the bigger extension algebra to itself, and I take the composite of g with f, that would give me a function from a to a prime to a prime. Well, there's a chain rule. In fact, g composed with f prime is g prime of f of p times g f prime of p. So this is a kind of mixed chain rule. So here's it in gory detail. dd zeta at the point p of that would be dg d zeta prime. That's the extension algebra variable differentiation evaluated inside function times df d zeta at p. All right. And here's the proof. The proof basically is to use the chain rule of advanced calculus, which says that the differential of the composite is the composite of the differentials. And then what's left is I need to prove the right linearity of the differential. And so that follows pretty fast because that pops out. But then I can pull the y out because we're assuming that g is a prime differentiable. So I can pull the y out, I think, is what I argue here. Yeah. And then, of course, when we plug in 1, we get that. So that's the chain rule. To summarize, the chain rule follows from the usual chain rule in advanced calculus and right linearity of the assumed functions. So what? Well, corollary. If we have an exponential function, we can look at the exponential function exponential alpha zeta, where alpha is a variable in a prime, and zeta is a algebra variable a. So the mapping zeta maps to exponential alpha zeta. That is a mapping from a to a prime, right? Where alpha, so alpha is an element of the extension algebra. Exponential of alpha zeta, that will also be in the extension algebra. So we're looking at a mapping, you know, again, just to be clear, the mapping is this. We're starting with zeta. We map to alpha zeta. And then we map to exponential of alpha zeta. So this is a prime, and this is a prime again. So, you know. So is this, if that's my f, you know, zeta maps to alpha zeta, is that a differentiable? Yes, multiplication by a constant is a differentiable. That's not a problem. Is the exponential? Is the mapping, this maps to, you know, this is straight up the exponential. It's w maps to exponential a w, if you will. Is that a different? Yes, the exponential is a differentiable. We've proved that. So, great. Definition. If we have p of x, a polynomial over a monic nth order polynomial, then the constant coefficient nth order A-ODE, p of d acting on eta equal to 0. This has characteristic extension algebra defined as follows. So what we do is we take a prime and define it to be polynomials in a over x mod the ideal generated by the characteristic polynomial. So this quotient is the quotient in which x behaves like a 0 of p of x. So it's x naught plus x1k da 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 plus xnk to the n minus 1. Do I have my, maybe that should be n minus 1. My numbering's off here. Sad. I should do x1. Anyway, if that should be maybe x1, that should be x2, that should be xn, or this has to be xn to the minus 1. Anyway, the numbering's off. All right, sorry. But yeah, I come on, man. Oh, I'm very annoyed by this. It's an n-dimensional extension. There should only be x1 through xn, or x naught through xn minus 1. The obvious typos need to be fixed. All right, sorry about that. The point is that algebra, we can look at the exponential and we can define component functions with respect. I mean, this takes 1 through k, 1k, k squared, da da da, kn minus 1 as a basis. And so I can expand the exponential in terms of f1, f2, da da da, fn, kn minus 1. Look, I got my numbering right down here, finally. And these should be analogous to sine and cosine for my motivating example, right? And those I define those to be the special functions of the exponential on A prime. And I would say that 1 through kn minus 1 forms a standard A module basis for A prime. And in fact, linear independence of this implies that the special functions defined above, in fact, are unique. And then here's the big theorem. Let p of x be a monic nth order polynomial in A, d the differentiation operator of the algebra. The special functions of the exponential for the characteristic extension algebra form a fundamental solution set for the nth order A-ODE, which is pretty much me saying I can solve any nth order A-ODE by taking a linear combination of these special functions. And the proof that we've built this up is pretty easy. It's really the calculus 2 proof. See, we take the polynomial, we feed it the exponential, but what's the differentiation operator do to the exponential? By the chain rule, it says, you know, the exponential times the derivative of the inside function. Derivative of the inside function, well, better to look over here. Derivative of the inside function pulls down the k, and that goes to e. So it's just what you've seen, you know, if we do the n-fold derivative of e to the kn, it's k to the n, e to the k zeta. And the same goes for each power, and so you factor out the e to the zeta, you got p of k, right? But in A prime, we have constructed A prime precisely so that pk will be 0. And so this is equal to 0, which is to say that e to the k zeta is is 0 like that, right? And then it follows that each of the component functions, because this is a linear differential equation, it follows that each of the component functions must also separately solve that being 0, right? I mean, so we must have each of the component functions, when acted on, are also giving us 0. And then I argue linear independence. I forget what's involved there, but oh, I actually had to go back and use the Wronskian here. So maybe we'll look at that next time a little bit, but I just want to show you an example, and I'll shut up for today. Check this out. This is really kind of neat. This is the repeated root differential equation, right? This is lambda squared minus 2 lambda plus 1. That's lambda equals to 1 2 times. How do we solve this in differential equations? We say, oh, e to the x is a solution, and then multiply by x. So x e to the x is a solution, right? My answer to us here is we look at the characteristic extension algebra, which is a plus bk such that k minus 1 squared is 0. Then I calculate the special functions of the exponential. I look at e to the kt, and this is a sneaky step. I want to make k minus 1 appear, because then that's this, And then this truncates because remember k minus 1 squared is 0. So I get that, which gives me e to the t times 1 minus t and t e to the t. These two are my special functions of the characteristic extension algebra, and those form a fundamental solution set for that. So I solved the repeated root case essentially by complexification, algebraification. And this one, if we were to solve and this one, of course, you can do just by integrating, right? But this would want you to, your A prime would just be span of 1 through kn minus 1 with k to the n equal to 0. So if you look at e to the zeta k in that context, it just truncates at k minus n1 order. And of course, 1 zeta, 1/2 zeta squared, 1 over n minus 1 factorial zeta to the n minus 1. Those are your special functions for that differential equation. Again, direct integration is faster, but it's kind of neat to see the nilpotent algebras coming into play and being useful for applications. See, this is a nilpotent algebra, right? It's got this basis element k. This k to the n is 0. That's a nilpotent element, and yeah. But anyway, I have more examples of this, and I should talk a little bit more about the linear independence next time, maybe. Maybe not. Maybe I should just let you guys read it. I don't know. You guys have any questions? No. So let's see. Next time I will try to talk more about the issue of how isomorphisms, how finding isomorphic algebras, how we can use isomorphisms to trade differential equations for other differential equations, and just these last couple of examples in this section. I think after that I'm pretty much done with this paper. I mean, I have another section on how to solve Cauchy-Euler problems over an algebra. Maybe I'll do that too. I don't know. But I do want to get back to the other papers. But in any event, thanks, guys.